Welcome. In AI data center design, scaling infrastructure often competes with maintaining peak performance. Today, we will explore the critical trade-offs between scalability and performance and how to balance them. Designing AI networks, we face a fundamental tension. Scalability aims to connect thousands of GPUs to handle massive datasets. However, performance in AI is defined by low latency and determinism. Because AI workloads use collective operations like all-to-all, the entire cluster waits for the slowest packet. This is the tail latency problem. Simply adding more switches to scale out introduces more hops and buffering, which can increase this latency. Must realize that a higher switch radix can connect more hosts with fewer tiers, but if not optimized with cut-through switching, it can lead to decreased application performance and lower return on investment. This chart illustrates the core conflict. As we scale up nodes on the left, we inevitably require more switches and tiers to connect them. This addition introduces higher latency and hops. For traditional apps, this is fine. But look at the bottom path. AI workloads demand low tail latency. The conflict arises because the added latency from scaling creates a performance drop, directly impacting the training time of models. To manage this trade-off, we treat fabric types differently. For the compute fabric, where GPUs exchange gradients, we cannot tolerate delay. Here we use a non-blocking full-fat tree topology. This ensures 1:1 bandwidth subscription, allowing every node to talk at full speed simultaneously. For the storage fabric, we can accept slight oversubscription, such as 5/4, to manage costs without crippling I/O. Crucially, just avoid mixing link speeds across tiers. Doing so forces switches to buffer entire packets store and forward, rather than switching them immediately cut through, adding unacceptable latency to AI training jobs. Here we compare the two fabric strategies. On the left, the compute fabric maintains a strict 1:1 non-blocking ratio between leaf and spine switches. This enables cut-through switching for minimal latency. On the right, the storage fabric uses a 5/4 oversubscribed ratio. This introduces some buffering risk, but achieves significant cost savings, balancing the budget while maintaining acceptable storage performance. Common misconception is that bigger buffers are better. In AI, deep buffers are detrimental. While they absorb traffic spikes, they increase the time a packet sits in the switch, driving up jitter and tail latency. Since AI jobs wait for the last packet, this delay stalls the whole operation. We prefer shallow buffer architectures that expose congestion immediately, triggering control mechanisms like ECN or PFC to throttle the sender. This keeps data flowing fast and predictably. Furthermore, utilizing a universal shared buffer prevents noisy neighbors from hogging resources, ensuring fair bandwidth distribution across all AI jobs. This visual contrasts buffer behaviors. In the deep buffer scenario, packets enter a large queue wait, leading to high jitter and ultimately a GPU stall. In the shallow buffer scenario, the packet moves through a fast switch. If congestion occurs, congestion signal is sent back, causing the sender to throttle. This proactive management results in consistent latency, which is vital for synchronization. To solve the scale performance equation, we use rail-optimized topologies. Instead of one giant mesh, we build parallel networks. All GPU 1s connect to rail 1, GPU 2s to rail 2, and so on. This keeps heavy synchronization traffic local to a specific rail, often reducing the number of hops data must travel. We combine this with adaptive routing. Unlike static routing, which can jam one link while others are empty, adaptive routing dynamically sprays packets across all available paths. This creates a balanced, high-bandwidth fabric that scales linearly, supporting the massive data movement needed for trillion-parameter model training. Here's the rail-optimized concept. Notice how GPU 1 from node and GPU 1 from node B both connect directly to the rail 1 network. They communicate without interfering with the rail 2 network used by the GPU 2. Within these rails, adaptive spray ensures traffic utilizes both spine S1 and spine S2 evenly, preventing bottlenecks and maximizing the total throughput of the scalable cluster.